9th Standard ICSE Physics Chapter 1 Measurements and Experimentation Part A Systems of Unit and Units in SI System. The first paragraph is cancelled. Then we have a definition of measurement. Measurement is the process of comparison of the given physical quantity with the known standard quantity of the same nature. For example, we know how long is 1 centimeter. That's a standard quantity. So if I want to measure the distance, then I just have to see how many centimeters long it is. That is, what is the multiple of a centimeter. Unit is the quantity of a constant magnitude which is used to measure the magnitudes of other quantities of the same nature. So in this example which I spoke of, centimeter is called a unit of distance, and the process of comparing and calculating is called measurement. So a physical quantity has two parts: the unit in which it is expressed and the numerical value. For example, the length of this pink line is around 8.5 centimeters. So 8.5 is a numerical value or the magnitude, and centimeter is the unit. Many more examples have been given here. Choice of unit. The unit should be of convenient size and there should be no ambiguity. For example, we can't use the thumb as a unit of distance. If you say that this is 1 thumb long, but everybody's thumb will have a different size. So there's a lot of ambiguity and confusion. Third, the unit should be reproducible. So if you have a unit like centimeter here, then people in other countries should also be able to create devices having 1 centimeter's length exactly equal to this length. Fourth, this value should not change with space and time. So if I take this ruler to the moon or in space, the magnitude of this distance will remain the same. It won't change. Units are of two types: the fundamental units and the derived units. This table is very important because it has the 7 fundamental quantities of science. Length, whose unit or SI unit is meter. SI means System International, that is international system, used by all scientists all over the world. Mass, SI unit is kilogram, and symbols are also given. Time, second. Temperature, Kelvin, not degree Celsius or degree Fahrenheit, but Kelvin, and no degree here. Luminous intensity is candela. Electric current, ampere, and amount of substance is mole. You will study more about mole in 10th standard chemistry. Here is a brief idea about it, which is not important in 9th standard syllabus, so you may cancel it. Now, apart from these, we do have 2 more complementary units: angle, which is measured in radian, not degrees but radian, and solid angle, measured in steradian. Solid angle is for 3-dimensional objects like a cone. So again, you will apply these in college level math and physics. All other physical quantities in physics are derived from these 7. For example, look at this table on page number 7, derived units. We know that area is length into breadth. Now length is measured in meters and breadth also in meters, so its unit is meter squared. So it is not a fundamental quantity. It is derived from the fundamental quantity of distance. Volume is also length into breadth into height, that is distance into distance into distance. So the unit is meter cube, that is SI unit. Of course, there are other units like liters, milliliter, centimeter cube, but SI unit is this. Density is mass upon volume. So mass is a fundamental quantity and volume is derived from distance as the fundamental quantity. Hence, density is also called a derived unit. So we can break up all these fundamental quantities into their elemental fundamental quantities. So we have so many derived quantities, but only 7 fundamental quantities. Your school teacher may give specific cancellations. As per ICSE syllabus, these definitions aren't important, but in certain schools they can be asked. A fundamental or basic unit is that which is independent of any other unit, or which can neither be changed nor can be related to any other fundamental unit. So length is independent of mass, time, temperature. Hence it's a fundamental quantity. Derived units definition. They are those which depend on the fundamental units or which can be expressed in terms of the fundamental units. I just showed you the examples of those. These examples mark it as read, which means you just have to read them, not learn them. Now the systems of unit. Earlier, we had three systems. The CGS system, which is a French system. FPS, which is a British system. MKS, or the metric system, which is in the same league as CGS system, with bigger units. And the MKS system has been extended to finally formulate the SI system. The MKS system only had three quantities: mass, length, and time. So M stands for meter for length, K stands for kilogram for mass, and second is for time. FPS, on the other hand, had same three quantities: length, mass, and time, but the units were different: foot, pound, and second. So second was same, but foot and pound are different from meter and kilogram. CGS systems had units which are smaller than MKS: centimeter, which is 1/100th of a meter; gram, which is 1,000th of a kilogram, but seconds was still used even here. So now we don't have just three fundamental quantities, we have 7 of them. This is to avoid confusion. If the British system is used in some countries and they measure things in foot and in pound, and the French system is used in other countries, then during communication between even common people, not just the scientists, there will be misunderstanding. That's why the SI system is used everywhere, especially in scientific reporting. Yes, these systems can still be used, but if there is confusion, they can always agree to work according to the SI system. Now, meter is just the SI unit of length. There are other units like kilometer, centimeter, bigger than meter or smaller than meter. So now we will understand the prefixes and their meaning. These are for the bigger units and these are for the smaller units. The last three of which can be cancelled. It's not important at all. So if I say decameter, the symbol is dA. So for meter it will be DAM. Decasecond will be DA and S. It means it is 10 to the power 1 times 1 meter. That means 1 decameter is equal to 10 meters. Hectometer is equal to 100 meters. Kilometer is equal to 1000 meters. Megameter is equal to 1,000,000 meters. Gigameter, that is capital G and small m, is equal to 1,000,000,000 meters. And terameter will be equal to trillion, and goes on. On the other hand, for the smaller units, we have decimeter, that is D, and then write the meter symbol M. It is 1/10th of a meter. Centimeter is equal to 1/100th of a meter, or you can say that 1 meter is equal to 100 centimeters. Millimeter is 1,000th of a meter. Micrometer is 1,000,000th. Nanometer is 1/1000,000th, and so on. But what if we want to convert one of these into the other? Let's take an example of micrometer. So we have 1 micrometer, that's the question. This is a symbol for micro, by the way, mu, is equal to how many kilometers? Now note, we are converting from a smaller unit to a bigger unit. Micrometer, what is the power for micrometer? It's 10 raised to minus 6. So let me just note it down, 10 raised to minus 6 meters. And kilometer is 10 raised to 3, 10 raised to 3. So it's always the first power minus the second power. So it will be minus 6 minus 3, that becomes 10 raised to minus 9. 10 raised to minus 9. So 1 micrometer is equal to 10 raised to minus 9 kilometers. So that's how we convert one of them into the other one. Let's take one more example. This time let's start with terahertz. Okay, so we have 1 terahertz is equal to how many decahertz? How many decahertz? So what is the power of terahertz? 12. And what is the power of decahertz? 1. So as I said, it's always the first power minus second power. That's 12 minus 1. That is 11. So the answer is 10 raised to 11. That means 1 terahertz is equal to 10 raised to 11 decahertz. Let's take one more example. 1 centigram is equal to how many picogram? So centigrams power is -2, picograms power is -12. So -2 minus -12, yeah, the first power minus the second power. That becomes minus plus, that is -2 plus 12. Sign of the bigger number is positive, so plus 10 is the answer. So the answer is 10 raised to 10. So 1 centigram is how many picogram? 10 raised to 10 picogram. So if you learn these tables, you will be able to convert anything into anything else. And here are some examples for that. Next, let's look at some of the units of length. The SI unit, of course, is meter. This is the old definition of meter. It's according to some alloy of platinum iridium kept in a museum near Paris. This alloy was used because it doesn't change its shape and size as per the weather conditions. But now we have a more accurate definition, which is independent of any material object. And this is the more accurate definition. But you can confidently cancel all this because it won't come in exams unless your school teacher specifies that he or she wants you to learn it. Maybe because they want you to get extra knowledge, or they just want to keep you busy. There are some sub-units of meter. Centimeter is 100th, millimeter is 1000th, micrometer is 1 millionth. We know all this. And how to convert centimeter into millimeter or vice versa, I just showed you the technique. Nanometer is 1 billionth of a meter. What about the bigger units of meter? Kilometer is equal to 1000 meter. And there are some non-metric units which are not mentioned in these tables. For example, astronomical unit is equal to 1.496 into 10 raised to 11 meters. This is used to measure the distance between heavenly bodies, nearby heavenly bodies. So its definition is, it is equal to the mean distance or the average distance between the Earth and the Sun, roughly 1.5 into 10 raised to 11 meters. Now, why average distance? Because the Earth's orbit is not exactly a circle, it's elliptical. So sometimes the distance between the Sun and Earth is less, and sometimes it is more. So if we take an average, this is the answer. Next, light year. It is the distance traveled by light in 1 year. Remember, light year or LY is a unit of distance, not time. It is equal to 9.46 into 10 raised to 15 meters. So we need to know these values as well. Cancel parsec and all of this, not in syllabus. There are some smaller units like angstrom. 1 angstrom is equal to 10 raised to minus 10 meters. It is represented by a symbol A with a circle on top. It is used to measure tiny things like the radius of a nucleus. And even smaller than that is a Fermi meter. Fermi meter is so small, 10 raised to minus 15 meters. In the table, femto was mentioned, but for distances we can use Fermi. So all of this is summarized in this pink table, which has to be learnt by heart, unless it is cancelled by your school teacher. Now let's talk about unit of mass. Kilogram is the SI unit, and this is the definition, which can be cancelled. Gram is 1,000th of a kilogram. Milligram is 1 millionth of a kilogram. Quintal is equal to 100 kg. And metric ton is equal to 1000 kg, which is 10 quintal. There are some non-metric units. For example, atomic mass unit, which is 1/12th the mass of a carbon-12 atom. This is used in chemistry to measure the masses of atoms and nuclei. Now, if we use kilogram, then it's such an inconvenient value, 1.66 into 10 raised to minus 27 kg. So to simplify things, we consider this as 1 atomic mass unit or Dalton. So 1 proton's mass is roughly this, and even 1 neutron's mass is roughly this. Electron's mass is far, far smaller than this. But why particularly carbon-12? Well, there is a history behind this. Carbon-12 atoms mass is 12. So carbon atomic number is 6 and mass number is 12 because it has 6 protons and 6 neutrons. If I take 1/12th of 12, that gives me the answer 1. So now I can compare any other atom's mass to this 1. So if you ask, what is the atomic mass of oxygen? Now I know that number of protons plus neutrons is equal to 16. So its atomic mass is 16. And atomic number is, by the way, 8. This is all chemistry, by the way. Or you can even say that an atom of oxygen is 16 times the mass of 1/12 the mass of carbon-12 atom. That is, it is 16 times 1. So these are all chemistry concepts, but now you know the use of atomic mass unit. Next unit is solar mass, which is approximately the mass of the sun, 2 into 10 raised to 30 kg. So we measure the masses of other stars with the help of this unit. This table is a good summary and you can learn this. Avogadro's number need not be learned in 9th standard. It is there in 10th standard, chemistry. The units of time, the SI unit is second. And the definition is, it is 1 upon 86,400 of one mean solar day. Mean means average. Which makes sense because one day is made up of 86,400 seconds approximately. All of this is cancelled and even this. Millisecond is obviously a thousandth of a second and microsecond is a millionth of a second. Shake, cancel it. Nanosecond is 1/billionth of a second. 1 minute is equal to 60 seconds. 1 hour has 3,600 seconds. 1 day is made up of 24 hours, which is 86,400 seconds. Lunar month, just remember one thing, that one lunar month or lunar cycle is equal to 29.5 days. The Gregorian calendar has the months of January to December. We know which months have 31 days and which have 30 days. February has 28 days, but in leap year it has 29 days. So 1 year is defined as the time which Earth takes to complete one revolution around the sun, which is roughly 365 days. The conversion of those 365 days into seconds is not important, cancel that. Leap year has 366 days. That's because this 0.256 days are accumulated every year, leading to one extra day after every 4 years. Cancel all of this. But remember, it is not necessary that if a year is divisible by 4, then that year will have a leap year. That rule has an exception called the century years, like 1800, 1900. If it's a century year, then just because it is divisible by 4, it won't necessarily be a leap year. We'll have to do one more test. Is it divisible by 400? If it is, then we can say it's a leap year, like the year 2000 or 2400. But if it's a century year and it's not divisible by 400, it won't be a leap year. For example, 2100 will not be a leap year. Why? Because of this Gregorian calendar which was invented. You have a better calendar, suggested in the physics community. Decade is equal to 10 years, century is equal to 100 years, and millennium is equal to 1000 years. Learn this table, but not these values which are cancelled. And finally, we have the derived units. We don't have to learn this column. And many of these quantities will be studied in later chapters. So you would understand these topics like electrical resistance and electromotive force only in the future. But right now, you need to just learn the definitions, that is your formulae, and their abbreviations of the units. For example, we've already studied the first three. Now speed or velocity is distance upon time, so its SI unit is meter per second. So either write it meter into second raised to minus 1 or meter upon second. Acceleration is velocity upon time, so that will become meter per second squared. Force is mass into acceleration, which is kilogram, and acceleration is meter per second squared. But we have a shorter unit called Newton. Work or energy, that is equal to force into displacement, which is joule, or kilogram meter square upon second squared. Momentum is mass into velocity, which is kilogram meter upon second, also called as Newton into second, because there is one more formula for momentum. Momentum, P, is equal to force into time. So that's Newton into second. That's how we get this. Notice that moment of force or torque is force into distance, and here work is force into displacement. So we're getting the same units of kilogram meter square per second square, and even here kilogram meter square per second square. But we can use joule for work or energy. It's a scalar quantity, but we can't joule here. We can only use Newton meter or this. If they ask for the SI unit, you have to write Newton meter, not this. Well, why can't we use joule here? Because this is a vector quantity. It's totally different from work and energy. Vector quantity means one which has direction. Scalar quantities don't have direction. As I said, all of this will be explained in future chapters in detail. Power is work upon time, so that's joule per second or watt. From 10th one onwards, these units are not so important. Go for the shorter units. They will be asked in exam. Pressure is force upon area, that's Newton per meter square or Pascal. But if you want to understand how we got this, then you look at the calculation here. Newton is kilogram into meter per second squared. And area is measured in meter squared. So 1 meter and meter gets cancelled, and then we are left with this. Frequency is 1 upon time period, that is 1 upon second or hertz. Notice that if the unit is derived from the name of a scientist, then the symbol should start with a capital letter. But if you're writing the full name, Hertz, H-E-R-T-Z, then don't start with a capital letter if it's a unit. Because if you do, then that will become name of a scientist. Same way Pascal, capital P here. But if you write full Pascal, then use small p. Because if you write capital P, that will be the name of the scientist. Electric charge is current into time. You will study this in chapter number 9. Current is a fundamental quantity. Ampere is a unit. And time is also a fundamental quantity. Second is a unit. So ampere into second. Even if you don't write the multiplication sign or the dot, it's okay. It's understood. It's multiplication. We have a shorter unit for this called coulomb. Again, the name of a scientist, Coulomb. For example, the electric charge of an electron is minus 1.6 into 10 raised to minus 19 coulomb. And for a proton, the same value but positive sign. Electric potential or EMF is simply the voltage. You know, when you buy a cell, it has a voltage of 1.5 volt. More the voltage, more the electric current which it can produce. So it's joule per coulomb because its formula is work upon charge. Again, you'll study this definition in chapter 9. Electrical resistance, well, when electrons flow through a wire, they have to face some hurdles. They bump into other electrons and other ions, which creates a resistance. The definition or the formula is potential difference, that is voltage upon current or volt upon ampere, and the shorter unit is ohm for resistance. Good conductors like metals have very low resistance. Bad conductors or insulators have very high resistance. That is why current can hardly flow through it. There's a traffic jam out there. And finally, electrical power. It's similar to power in that the SI unit is watt, but the definition is different. Here it is potential difference or electric potential into current. That is volt into ampere. The guidelines for writing the units, just mark it as read. You don't have to learn it. First of all, they talk about when to use small letters and capital letters. I've already explained that. There is one exception. Liter has capital L because small l looks like 1. So even though liter is not a name of a scientist, still we use capital L for the unit. Here they have explained why multiplication sign is not necessary. And you may write a negative power for something which was supposed to be in denominator, but don't write like this. If you write meters per second, don't write meter per second inverse. No. Either just write meter per second or put the second inverse in the numerator. These are laws of indices involved here. Also, we don't write in plural. We don't say 10 meters in physics. We just say 10 meter. Because if we write meters and put an S here, it looks like meter into second. Also, we should know when to use small letter and capital letter. Like kilo has small k, but mega and giga have capital M and G respectively. Also, we should know how to convert units when powers are involved. For example, 1 meter is equal to 100 centimeters. But 1 meter square is 100 square centimeters square. That is 10,000 centimeters square. Now tell me, 1 meter cube is equal to how many centimeter cube? Think about it. Well, it will be 100 cube. That will be 10 raised to 6. That is million centimeter cube. So when you do numericals, you should be careful about conversion.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.